Okay, we're going to finish up talking about gases. So chapter 9. So we ended right before this slide. So now we're going to talk about what if you have mixtures of gases. So the total pressure exerted by a mixture of gases in a container at constant volume and temperature is equal to the sum of the pressures of each individual gas in the container. So we're going to see with Dalton's law of partial pressure that it really doesn't matter if you have a mixture, because PV equals nRT doesn't have any information about what type of gas you have. So whether or not you have nitrogen or hydrogen or a mixture of the two, it doesn't matter. The pressures will be the same as of the individual gases added together. So we're going to use an idea or another concentration unit, essentially the mole fraction. So let's say we have hydrogen and nitrogen, and we want to know the mole fraction of hydrogen. So that would be the moles of hydrogen over the moles of hydrogen plus the moles of nitrogen. So the total moles in the mixture. Mole fraction is given in X. So Xi is the mole fraction of I, equal to the number of moles of I divided by the total number of moles. So the big thing with Dalton's law of partial pressures, and looks like they're not going to talk anymore about this, but we will talk more about it in class, is that if the ideal gas law doesn't care about what kind of particles you have, you can use the ideal gas law for a mixture for the whole thing, for the individual components. So you could calculate the total pressure if you knew the total number of moles. You could calculate the pressure of the hydrogen if you knew the number of moles of hydrogen, the pressure of nitrogen. So you can use the ideal gas law for the whole mixture or for the individual components. So the kinetic molecular theory of gases is really helping you have a little better understanding of what a gas looks like when you look at the individual particles. So a gas consists of tiny particles, either atoms or molecules, moving about at random. So there's a lot of movement. The volume of the particles themselves is considered negligible compared with the total volume of the gas. So most of the volume of a gas is empty space. And the ideal gas law assumes that the volume of the particles is zero, and that you put a mole of gas into a container that's a liter, and you still have a liter of empty space. Number 3, the gas particles act independently of one another. There are no attractive or repulsive forces. So really says there's no potential energy. There's kinetic energy of their movement, but when the particles see each other, they're not attracted or repelled, so there isn't a potential energy term for their energy. Collisions of the gas particles, either with other particles or with the walls of the container, are elastic, which just means they don't change the overall energy of the system. And the average kinetic energy of the gas particles is proportional to the Kelvin temperature of the sample. So temperature goes up and the kinetic energy goes up. This is just a summary. So decreasing the volume of the gas at constant N and T increases the frequency of the collisions with the container walls. Increasing the temperature at constant N and P increases the volume of the gas. So I guess this is just a summary. It's not the kinetic theory, but just a summary of what we've learned. Increasing the amount of gas at constant T and P increases the volume of the gas. Dalton's law says changing the identity of some of the gas molecules at constant T and V has no effect on the pressure. So it doesn't matter if they're all the same as long as you know the number of total gas particles. So the kinetic molecular theory of gases helps you understand things like the relative speeds of different gas molecules. So heavy things go slower at the same temperature. So if the kinetic energy is proportional to temperature, which we said right here in number 5, then it doesn't matter what kind of particles you have. And so if kinetic energy is 1/2 mv squared and it's directly proportional to temperature, then the kinetic energy of hydrogen, helium, water, nitrogen, oxygen, carbon dioxide are all the same at the same temperature. So that means in order to think about keeping that constant, 1/2 mv squared has to be proportional to T in the same way for each of these. And if the mass is bigger, that means the kinetic energy will be, or the volume will be, the velocity, it's a V, will be less in order to keep mv squared the same. So carbon dioxide is the heaviest thing here. So it's going to have the lowest average speed at the same temperature, and hydrogen is the lightest, so it's going to have the highest one. So 1/2 mv squared has to stay constant. The mass is going up as you go from hydrogen to carbon dioxide, therefore the velocity has to be going down. And so this is just a picture of the distribution of speeds at different temperatures. So as temperature goes up, the average speed goes up, and the curve also flattens out some. So if kinetic energy is proportional to temperature, this is essentially just giving you insight into how it changes with temperature. So you can take advantage of the fact that gas particles move at different velocities at the same temperature based on their masses. And so diffusion on the left-hand side just shows you that diffusion is the mixing of gas molecules by random motion under conditions where molecular collisions occur. So it's just looking at these two gases will mix completely over time. A fusion is a whole nother process. It's a process that you can use to separate gases. So if you have an empty container and a gas on the other side, and you put a small hole in the wall between the two, the heavier the particle, the slower the velocity on average. And so you're going to get the lighter particles on average going through the hole more often. So you're going to be able to separate out the light things from the heavy things just based on their relative velocities at the same temperature. And so we'll give some examples. This was an important process. It still is an important process to separate the isotopes of uranium so that you can make them into either fuel rods for nuclear reactors or into bombs for warfare. So it's a pretty important process, and it's used to separate those isotopes. And so the rate at which the molecules go through that hole is going to be proportional to 1 over the square root of the mass. So we know that as mass goes up, their velocity goes down, so the rate should go down. So they're inversely proportional. The square root comes into play because it's velocity squared, if you look at deriving the equation. So we will do lots of problems with this particular equation in class. So the last thing in the chapter is just talking about the fact that if you go all the way back here to this guy, notice that the molar volumes aren't exactly equal. So PV equals nRT is an approximation. It's a pretty good approximation, but the properties of the gas molecules do impact pressure, volume, and temperature relationships. And if the pressure is too high or the temperature too low, then you'll end up with behaviors that are very different than the ideal gas law. So if you think about it, at low pressures, the gas particles are far apart. So it's a pretty good approximation to say that the space is mostly empty and they're not interacting with each other. But if you increase the pressure, the particles are close together, they start attracting and repelling each other. And so you start getting deviations from that ideal gas equation, and you need to use an equation that corrects for that, corrects for interactions. And so the attractive forces between particles become more important at higher pressures because they're just closer together. So you can either have attraction or you can have also repulsion, depending on how close together they get. So the equation that we're going to use in our book, there are lots of different ways to correct an equation, but this is called the van der Waals equation for real gases. So we think about this equation. This says that P plus some other correction term for the attractions between molecules, times V minus a correction for the fact that the particles actually take up space, so you don't still have an empty flask when you put some particles in. That left-hand side equals nRT. So if the intermolecular attractions are small, so small that they could be called zero relative to pressure, then we have pressure in that set of parentheses. And if the volumes are super small, and we can approximate it as zero when you subtract it from volume, then you end up with P times V equals nRT. And so you're back to that ideal gas law. So these are just two correction terms for situations when the gas particles do interact with each other and they do occupy some of the volume. The last bit in the chapter is about pollution and then also about global climate change. This is just a set of graphs that shows you what changes as you go up in altitude. So the atmospheric pressure decreases as altitude increases, and the average temperature varies irregularly with altitude. So those are two things that have a huge impact on what our atmosphere looks like. So the concentration of atmospheric CO2 has increased in the last 160 years, and I'm pretty sure you all know that. It's gone from 290 parts per million in 1850 to the current value of 400. So we're clearly changing the Earth's atmosphere by burning fossil fuels. So we learned in chapter 8 about thermal chemistry and how when we burn octane or methane, we make CO2. And so CO2 is a very stable molecule. It exists for a long time. I think I've heard 100 years, and that I don't know that they mentioned that in your book. So as it goes up, it doesn't change, it stays in the atmosphere. So the greenhouse effect is caused by the absorption of heat radiation in the Earth's atmosphere. So molecules like CO2 and methane, within their bonds, they can absorb infrared radiation and get hot, essentially, vibrate with more energy. And when they do that, they trap the Earth's heat and it doesn't escape out of the atmosphere. And so the Earth warms. So O2 and N2 are gases that don't absorb infrared radiation, and it is because of their dipole moment, which if you take upper level classes in chemistry and physics, you'll understand why that's true. But the natural O2 and N2 in the atmosphere don't act like greenhouse gases, but these other molecules that are a result of combustion, CO2 and methane, comes from all sorts of places. Some of it's just leaked when we are mining for petroleum. So the term climate change denotes warming on a global scale, but greater extremes of hot and cold and seasonal storms. And if you watch the weather, it's very interesting because I've been teaching about climate change since the late 80s. And there used to be just a little mock video I'd always show that was a news clip from the future back in the late 80s. And it was all about there are fires and there are floods and there are extreme hots and colds. And right now, from my point of view, the weather I watch that's the real weather, or the real news, is basically what they were projecting climate change was going to cause. All these extreme events, from more hurricanes to just more hot weather to floods and definitely the wildfires. So carbon dioxide is emitted through numerous industrial chemical processes, and the amount of CO2 emitted is referred to as a carbon footprint. So if you take environmental science, I know that's one of the things you do in the global climate change class is calculate your own carbon footprint, look at what you do in a day on average, and decide what your impact is on climate change. And so that is all of chapter 9, and we have one chapter left on solids and liquids.